Hello and welcome to another presentation, this time on Rcos or sine x plus or minus alpha, a very special format which helps us solve certain equations and certain problems. Let's take, for example, an equation like this. Now, this equation, if you graph it on GeoGebra or something like that, you will notice it looks very similar to a sine or cosine curve. In fact, hopefully you'll notice that it's simply a sine or cosine curve, depends which one you want to use, simply translated in the x direction by a certain number of units and then stretched in the y direction by a certain scale factor. And that's because anything of the form a cos x plus or minus b sine x, where a and b can be any constant numbers, anything of that format is in fact just a stretch in the y direction and a translation in the x direction. And therefore it should be possible to write this in the form Rcos x plus alpha. Now, I want to straight away say that that could have been R sine x minus alpha. We can use coses or sines for this, but the question almost always, in fact I'm going to say always, tells you the format it wants it in, mainly to help the people who are marking the exams because they don't want two different ways of doing it. But that's specifically why we use this R cos x plus alpha format. It helps us understand the function better. Now, if it does equal that, we should be able to determine the value of R and alpha, and that's what I'm going to ask us to do first. We're going to determine the value of R and alpha for which that is true. And let's do that first. And it will be the smallest possible value of alpha I'm looking for, the smallest positive value, because naturally there are an infinite number of values of alpha for which that is true. Okay, so this is the way I normally proceed to answer this kind of question. What I'm going to do is on the left hand side, I need to determine R and alpha, and I'm going to do that by using the compound angle formulae and then equating coefficients. So firstly, I'm going to use the compound angle formulae for cos, and as you can see, that gives me R, open brackets, cos x cos alpha minus sine x sine alpha. And now my approach is going to be to equate coefficients, because as you can see, when I multiply through the brackets by R, my R cos alpha, because it's being multiplied by cos x, that should be the same as 5. So I can deduce straight away that R cos alpha is 5. Similarly, when I multiply R by sine x sine alpha, I'm going to get R sine alpha equals 3. And now what I'm left with is two equations with two unknowns, R and alpha. Now, I like to point out to my students that this is really just a right-angled triangle problem like this. As you can see, I've written R on the hypotenuse, and that's because I could easily rearrange, for example, cos alpha to be 5 over R and sine alpha to be 3 over R. And for cos, it's adjacent over hypotenuse. For sine, it's opposite over hypotenuse. And so I can rewrite it like that. Because then it should be obvious why R is 3 squared plus 5 squared. Because of Pythagoras' theorem, or square root, sorry, should I say, 3 squared plus 5 squared. And so that's going to give me root 34. And then for alpha, now I really should have said in the question that we're working in degrees here, but we could be working in radians, but the question should tell you that. Let's just say that we're working in degrees. So x is between 0 and 360, because I'm going to solve a question in a second with it. First let's find R and alpha though. And I'm now going to try and find alpha. Well, the simplest way of doing that, if you ask me, is to just say, well, tan alpha, from dividing those two equations, or if you like, just from the diagram, tan alpha is 3/5, and therefore alpha is going to be inverse tan of 3/5, which comes to 31 degrees, correct to the nearest degree. Now, let's just go through a few things about what that tells me, because that tells me lots and lots and lots of interesting information. It means my original function is really exactly the same as the cos graph stretched by root 34 in the y direction and also translated 31 degrees to the left in the x direction. It is the cos curve but moved 31 degrees to the left and stretched by a factor of root 34 in the y. That's really handy to know, especially for the next question I'm going to ask. Okay, so this now puts us in a position. Now we know 5 cos x minus 3 sin x is identical to, and I could put in an extra line on my equals there, identical to root 34 cos of x plus 31. Although it's only roughly equal because I did round to 31. We can now do things like find the maximum value of 5 cos x minus 3 sin x. And it doesn't take any working out at all. Because if 5 cos x minus 3 sin x is exactly the same as root 34 cos x plus 31, well, I always say to my students like this, what's the maximum value of cos x? It's 1 and minus 1, isn't it? Cos x fluctuates between 1 and minus 1. Does that value change if I move it left or right, the maximum value of the curve? No, it's still trapped between 1 and minus 1. Okay, what about 2 cos x? Well, that's trapped between 2 and minus 2. 3 cos x, that's trapped between 3 and minus 3. And so root 34 cos of stuff, well, that's going to have a maximum value of root 34. And what's more, I can even determine the smallest value of x for which this maximum occurs. I can just kind of think about it in my head really, because cos x has a maximum of 1 normally at 0. But if I move it back 31 degrees, well, its maximum is then going to occur, if I'm looking for the smallest positive value, it's then going to occur when x is 329 degrees. And you can check that on a calculator as well. If you now do 329 plus 31, you'll have 360, and cos of 360, sure enough, is 1. Times it by root 34, yes, you've got the maximum value, which is root 34. And so that's why this special format is so convenient. Now, the other reason why this is convenient is to solve equations involving 5 cos x minus 3 sin x. Let's take a quick example. Let's solve 5 cos x minus 3 sin x equals 4 for 0 to 360. Well, all we do is we use our new format, root 34 cos of x plus 31, which equals 4. And then we divide by root 34 and inverse cos. So x plus 31 is going to be equal to inverse cos of 4 over root 34, which does in fact equal the following. Now I get 46.7 when I press inverse cos on my calculator, but remember, resist the temptation to take away 31. First, you've got to do your rule of thumb for cos, which is 360 minus, and I get 313.3. And now I can take away 31 from both those answers, and so I'm going to end up with 15.7 for the first one, and 282.3 for the second value. Now, what I really like telling students is please do plug that last one back into 5 cos x minus 3 sin x and see how close you are to 4. And I've just plugged that last value into my calculator and I'm very, very close to 4. I'm at 3.997. And so I know I've done it correctly. That completes this short presentation on r cos theta plus alpha, or r sin theta plus alpha. It's a lovely little format to write your equations in. It's not too tricky really. The main thing is to recognise after using the compound angle formulae that you've just got a right angled triangle problem. But it's a very, very useful format, so yeah, make sure you've got your head round it, and best of luck with this kind of work in the unit assignment. Thank you for listening, and yeah, I will speak to you soon in the next presentation.